Hello. In this presentation, I am going to talk about job scheduling on Ibex. HPC resources must be kept busy at all times to maximize the scientific impact of machines like Shaheen or Ibex. Fairness of distribution of computational resources in such circumstances is also paramount. To achieve these objectives, job schedulers are used. In general, job schedulers allocate resources to jobs for a certain amount of time from a resource pool. This allocation and its usage is maintained and accounted by the job scheduler. This helps the scheduler to manage priorities of jobs. Using job scheduler on Ibex may need some changes to your workflow. Job schedulers run work on your behalf. This means you may need to script and automate your workflow. A benefit of doing so is that you can submit multiple experiments or your simulation jobs all at once and maximize throughput of your scientific investigations. The allocatable resources on Ibex include compute nodes of various microprocessor architectures and with different memory capacities, heterogeneous compute nodes with GPU accelerators of various microarchitectures having 4 or 8 GPU cards per node, an assortment of large memory compute nodes with maximum memory capacity of 3 terabytes on a single node, and local SSD storage on some compute nodes. These allocatable resources are pooled in queues with limited maximum wall time. A smaller pool of resources is set aside for debugging and prototyping purposes with limited scale and short duration. On Ibex, we use SLURM for job scheduling. SLURM primarily allows to schedule more work than available allocatable resources by managing the submitted jobs in partitions or queues in running or pending states. It also provides mechanism to manifest complex workflows. For example, dependent jobs or an array of parameterized jobs. SLURM provides a means of describing and submitting a resource request, configuring the use of allocated resources to match the capability of the user's application, a means of monitoring the job status, and accounting the use of allocated resources. Let's now jump into how user can interact with SLURM. First, let's see how to query the status of system resources. sinfo is a useful SLURM command which shows a concise report of the resources and their states. Available partitions or queues are listed in the first column. We'll be using the terms partition and queue interchangeably. The second column shows the status of this partition. The third column lists the maximum allowed wall time for a job submitted to the partition. For example, batch partition allows a maximum of 14 days of wall time for a submitted job, whereas the debug partition allows jobs with maximum wall time of 2 hours. Fourth column shows the number of nodes in the specific partition and the state of these nodes shown in fifth column. The last column shows the list of node IDs belonging to the partition. For convenience of our GPU users on Ibex, the Ibex team has developed an in-house query tool to show the available GPUs by their architecture. You can run with -- help to list all the options for G-info. To show the list of scheduled jobs on the system, along with their states and job IDs, the command sq is used. By default, sq lists the jobs by all the users in any state, may it be pending, running, or completing. The output of sq can be filtered by username or job ID to get more concise and relevant view. SLURM provides a means of describing an allocation request as a collection of directives, parameterizing the resources, including accounting and time requisites for the submitted jobs. Partitions or queues are pools of allocatable resources pooled under global constraints such as maximum time or minimum or maximum job size. Ibex Cluster is composed of nodes with different CPU and GPU microarchitectures. Constraints or features are convenient labels to assign to nodes of same configuration so that a user can request compute resources of particular microarchitecture if they choose to. For example, you may want your application to run on Intel Cascade Lake nodes or NVIDIA V100 GPUs. These features can be added to resource request and submitted to SLURM for appropriate scheduling. Allocation requests can constitute of computational resources and duration for which they are needed for your job. CPUs, GPUs, and memory are the three allocatable resources, and wall time is the expected time your application would require these computational resources to be available. Users can submit their work as batch job to SLURM or request the computational resources to run their work interactively. Batch jobs are composed of resource request and workflow steps to run when the requested resources are available, all in a JobScript. Once submitted to SLURM, it will execute the JobScript on user's behalf when the requested allocation is granted. For batch jobs, the wall time can be set for long durations, and multiple jobs can be submitted if needed. In cases where the user wishes to prototype or debug a workflow, interactive jobs or sessions can also be submitted. In this case, a resource request is submitted and control of the prompt is given back to the user to run the workflow steps interactively. Since these sessions are generally used for prototyping and debugging workflows, they are small in scale and short in duration. Let's now examine an example JobScript which, when submitted to SLURM as batch job, will run on user's behalf. The first line starts a new shell, in this case, a bash shell. The next lines, starting with #sbatch, are directives to SLURM. The srun command in this script will launch our CUDA application here called Hello World on requested resources when they are available. This job can be submitted to SLURM using a command called sbatch. Sbatch is a command to submit batch jobs to SLURM. A Upon successful submission, it returns a job ID assigned to the submitted job. Upon being queued to a specified partition of SLURM, the job gets scheduled and a priority value is assigned to it. The priority increases with the age of job in partition. In general, jobs requiring small number of nodes and short wall time are easier to schedule for the scheduler and will run before the others. Users can cancel a submitted job in any state using the SLURM command scancel. Scancel requires job ID as its argument. For submitting resource requests to start interactive sessions, the SLURM command salloc or salloc is used. For example, if I need a CPU and a GPU of type V100 from debug partition for 10 minutes, I'll pass this resource request to salloc as its arguments. Once the job is allocated, SLURM will notify by a message granted job allocation and a job ID. I can now launch my application on the resource allocated to my job ID using the srun command. The environment I load will also be passed to the remote resources allocated to my interactive job. The allocation persists even after the srun command finishes. I can run further steps of my workflow with more srun commands. Once finished prototyping, I type exit, which terminates the interactive session. SLURM allocates the requested resources to a job. The use of these resources can be configured to best suit the multiple steps of workflow. Let us look at an example of an interactive job asking for 40 CPUs in total from debug partition for 10 minutes. This is to run a hybrid MPI and OpenMP application. Once allocated, the SLURM command srun can be used to configure the available resource to launch the job. In this example, srun command launches a pre-processing step on a single CPU. Once completed, the next step with 4 MPI processes, each capable of spawning 10 OpenMP threads, is launched. Once this step is completed, we can exit from the granted allocation to terminate the job. Jobs, once submitted to SLURM queue, can be monitored and their accounting can be queried too. sq is a SLURM utility to query the status of a submitted job. By default, sq shows all jobs in SLURM partition. It can be filtered by user or by job ID for concise view of output. scontrol is another useful SLURM utility to query the details of a job during its lifetime. When the job finishes, normally or otherwise, scontrol will not be able to retrieve this detail. Among other things, it lists parameters such as node list allocated to the job and details of resources allocated. It is good practice to call scontrol command inside the JobScript to snapshot the resource allocation. sect is another powerful utility to query the accounting associated to the usage of a job or jobs by a user. By default, sect shows all the jobs run in the recent days by a user invoking the command. You can filter the output by job ID or by user or even by partition. Sect shows a job and all the job steps associated with it. Let us now visit some example job scripts which are a commonplace on Ibex. This is a job script to run a job with 4 OpenMP threads on Ibex compute node. Minus CPUs per task ensures that the parent process of the application hello world underscore OMP has 4 physical CPUs or cores available to spawn 4 OpenMP threads when the application needs it. The srun command with -C4 then makes use of this resource and launches the application. This is an example of MPI job to launch 32 MPI processes on the same node. The job therefore requests --n tasks equals 32. In addition to this, the SLURM directive --n tasks per node equals 32 requests that all the 32 cores should be allocated on the same compute node. --constraint directive requests a compute node with processor which is of Intel architecture. Together with request of 32 n tasks and the constraint, SLURM will ensure that a compute node with at least 32 cores of Intel architecture is allocated to a job. For allocating large memory node to the submitted job, the directive --mem can be used. Standard compute nodes in Ibex Cluster have a maximum of 360 gigabytes of allocatable memory. Setting --mem directive to more than 370 gigabytes indicates to SLURM that a large memory node is required for this job. Upon successful submission, the job will be tagged by SLURM as a large memory job. Note that if memory is not explicitly added to SLURM directives using --mem, the scheduler will allocate a default memory of 2 gigabytes for each core requested. To run CUDA applications on GPU nodes of Ibex, --grez directive must be added to the job scripts. --grez, or generic resources, takes a colon-separated pair of device label and the required number. For example, in this job script, we require one GPU of type V100. Since we know that our application hello world underscore CUDA requires at least 64 gigabytes of host memory, we will add this to our job script as well. Finally, the srun line will ensure the application is launched on the allocated resources. Similar to our previous example, here we request 4 GPUs on a single Ibex node. We ask for 4 cores on host so each GPU is fed data by a dedicated core running one of the 4 processes. Finally, srun command launches the 4 processes on CPU host. In this example JobScript, it is assumed that our application hello world underscore multi GPU is a CUDA aware MPI application. Shown here is a list of common constraints used on Ibex to access different microarchitectures of CPUs and GPUs. For instance, to allocate any Intel microarchitecture, use constraint equals Intel. To specify a particular Intel architecture, you'll use the name of the architecture, such as Skylake or Cascade Lake. For allocating a GPU of particular microarchitecture, use a combination of -graz and constraint. To request large memory nodes, use mem directive. Local storage, that is, disk space on local SSDs on the compute node, can be allocated using the constraint local underscore the storage capacity required. For example, local underscore 500G will get you 500 gigabytes of local storage mounted as tempfs. You may need this for some I/O intensive applications. Note that this storage, as the name suggests, is local to a compute node and cannot be accessed by a process running on another compute node. In some cases, you may want to know why your job is queued for long duration but has not started. The output of sq command filtered with the job ID shows reason for which the job is held pending. To see more details on the possible reasons reported by SLURM and their meaning, visit the manual page of SQ by typing man SQ and search for job reason codes.